In chemistry, there's basically two kinds of reactions when it comes right down to it. And the one kind that we talk about a lot is when you have an atom being transferred or a group of atoms being transferred. And this is an example here of acetic acid reacting with water. It makes the acetate ion and hydronium. And we've talked about this reaction a lot already, but this is an example of an atom being transferred. It's being transferred from the acid, acetic acid, to the base water to make the conjugate base acetate and hydronium. So this would be an example, and it could be a group of atoms like a polyatomic ion or something, but this is a very common kind of reaction. The other kind of reaction, though, which is very important, especially in this chapter, is electron transfer. And in an electron transfer reaction, you have to have one atom or group of atoms contributing an electron and one atom or group of atoms accepting the electron. In this reaction that's shown is donating electrons to silver plus ions. And I know that for two reasons. Number one is that copper on the left doesn't have a charge, and copper on the product side does have a charge, positive 2. So that means that each copper atom has donated 2 electrons, and it has become a positive 2 charge. Silver plus is becoming less positive. You can see that silver is going from a positive 1 to a 0. So that means that each silver ion, each silver plus, is gaining an electron to become silver metal, silver with all of its electrons. There are 2 silvers there, 2 silver pluses, because you need 2 to take the 2 electrons from the copper. When you're writing an electron transfer reaction, by default, you don't show the electrons. And if you only had 1 silver plus going to 1 silver, you'd have like an extra electron floating around somewhere. And that's seen as bad form in chemistry. We'll talk about half reactions, which is when electrons can be shown, but overall electrons, you don't show them in the reaction. So electron transfers at first might look similar to the atom group transfer reactions, but they're actually quite different. And we're going to focus mostly on the electron transfer reactions in this chapter. In this reaction between copper and 2 silver plus ions to make copper 2 plus and 2 silvers, what you can do if you really want to see those electrons, and there will be times that we want to, is you can break them down into half reactions. And in a half reactions, you can show electrons. Now, if you write the half reactions correctly, one of the half reactions will have electrons as products, which means electrons are being given up by the reactant. So in this first reaction right here, copper metal is giving up 2 electrons. All right, copper 2 plus is created and 2 electrons are products. So copper literally is giving up 2 electrons. And in the other reaction, you should have a chemical taking the electrons that are given. And in this reaction, definitely 2 silver pluses are taking those 2 electrons, to make the 2 silver metal atoms. So in half reactions, you should see one chemical species giving up electrons and one chemical species is taking the electrons. So with that, in the overall reaction, when you combine them, you won't see any of the electrons at all. Electron transfer reactions are officially called oxidation reduction reactions. And this is something we looked at in Chem 221 in one of the sections between chapters 3 and 4. Oxidation reduction reactions are often condensed down to redox reactions. So a redox reaction is an electron transfer reaction. And in a redox reaction, you have something being reduced and something being oxidized. So that's where the redox comes from, I guess. I don't know. Redox reactions are pretty cool. And if you do the redox reaction correctly, you can actually create electric current, all right? So if you plug something into the wall outlet, you're getting electricity from it. You can have a chemical version of that's creating that current. And that's kind of a cool thing. This is the general idea of like batteries, for example. So this field is oftentimes called electrochemistry. It's electric current or electric power, if you will, being created from a chemical means. These redox reactions can be really, really helpful. There's lots of terms in Chem 221, and I want to talk about them real fast. Oxidation, reduction, oxidizing agent, and reducing agent. Oxidation is when a chemical loses electrons, and it increases the oxidation number. A reduction is when electrons are gained, and you have a decrease increase in the oxidation number. If you don't remember oxidation numbers, we'll talk about that here in a little bit. But for right now, oxidizing is to lose electrons, reduction is to gain electrons. In the back of your mind, oxidizing agent is something that's accepting electrons. It's a species that's been reduced, all right? And so if something is reduced, it's also known as an oxidizing agent. And if something has been oxidized, it's also known as, you guessed it, a reducing agent. I find the last two very confusing. Remember that if it's an agent, it does the opposite. So an oxidizing agent is reduced and a reducing agent is oxidized. And that's pretty crazy. I prefer my lion, and this is a lion I showed in Chem 221. I called him Leo the lion, and Leo says grrr, and sound effects not necessary. Leo says grrr is an acronym. Leo stands for lose electrons oxidized. Grrr stands for gain electrons reduced. So in the bottom down there, you see there's zinc metal. It's losing 2 electrons, so zinc is being oxidized. On the other hand, the copper 2+ is gaining electrons to make copper metal. It's being reduced. So Leo says grr is the way I like to roll, but you can do it either way you want. You can also use oil rig. Oil rig is another acronym. Oil means oxidation is losing. Rig means reduction is gaining. And honestly, either way you want to do that, fantastic. Which species is being oxidized in the following reaction? When it asks a question like that about what's being oxidized, what's being reduced, it's always relative to a reactant. So you wouldn't consider Ni2+ or the Ag solid. All right, those are both products. Those would be exempt. Now, something that's oxidized, it's lost electrons. So there's a couple different ways to do this. What I do is I see, for example, that nickel starts at a nickel without a charge, and that's the nickel solid. And on the product side, it goes to nickel 2+. Now, the only way an element can go from a 0 to a positive 2 is if it loses 2 electrons. So in this problem, the thing that's oxidized is definitely the nickel, all right? The nickel has lost electrons. Silver is going from a positive 1 on the reactant side to a 0. So silver plus is going to take an electron to become silver 0. All right, you can't do that. Now, another way you can do this is you can look at the oxidation numbers. Now, if an element or species doesn't have a number next to it, for example, nickel solid, that means it's a 0. So nickel is going from a 0 to a positive 2 on the product side. If the oxidation numbers become more positive, that means it's being oxidized. Conversely, the silver is going from a positive 1 on the reactant side to a 0. So silver is becoming less positive. That means that something has been reduced. So any way you want to do this is fine, but you should at first definitely make sure you know how to recognize if something is oxidized or if something is reduced. You can always go back and look at the oxidation numbers from Chem 221, but I'm also going to show you some hints in here about how you can kind of get away without doing that. More in a minute.
Copper metal reacts spontaneously with a solution of silver nitrate. A coating of silver metal forms on the copper, while copper 2+ ions, which are blue in water, are released into the solution.
This is a reaction between copper metal and silver ions, and once in a while when the price of silver has been pretty high, this is a reaction that people will do. They get the pure silver, that kind of mossy looking stuff. Pure silver comes out very unorganized, not like silver jewelry or something like that. Anyway, they can take that raw mossy silver and then sell it and make lots of money. Whoopee-doo. Anyway, this is a redox reaction. Copper is becoming copper 2+. Copper here is losing electrons, it's being oxidized. Conversely, the silver plus is going to silver 0, elemental silver. So silver is gaining the electrons that copper is giving up. Silver plus is being reduced. All right. So this is a redox reaction, but notice how all of the reaction occurs on the surface of the copper. Copper was kind of that spiral metal right there, and the silver you can see is forming on the spiral parts of the copper. copper. This is what they call a direct redox reaction. And if you're using redox to make chemicals, all right, this is actually a really cool way to make chemicals. The reaction occurs on the surface of the reactants. You usually have pretty high yields, especially if you're patient and stuff, and that's kind of cool. There are other types of redox reaction that offer scientists some cool possibilities, and we'll see that here in a little bit. This is just a more detailed example here of what's going on. On the left-hand side in the beaker, you see the copper metal, and the copper metal there is just like that spiral kind of thing. You add some silver nitrate, which is a solution with silver ions, and initially it's a clear liquid, but after not a very long amount of time, you can see in the middle picture that the liquid begins to turn a slight blue, and you also begin to start seeing little silver pieces on the copper. Silver plus ions gravitate towards the surface of the copper, and at that point, the electrons from the copper are transferred to the silver ions, making silver metal. And in the process, the copper ions are released. That blue color is indicative of the copper 2+ ion. It's got kind of a neat light blue kind of color. And as the reaction proceeds, you have more and more copper 2+, less and less silver ions. The silver, though, does show up again as that kind of mossy silver right there. Pure metals, when they're first formed, aren't nice and compact sometimes like silver here. So you can see that's what it looks like. It kind of looks like an underwater landscape. I don't know. I have excitement. Anyway, if you wish to have more control over your redox reaction, you can institute what's called an indirect redox reaction. And an indirect redox reaction means that somehow you're going to separate the side that's being oxidized and the side that's being reduced. And you can do that by using an external wire. Copper, metal, and a couple other metals are really good about transferring electrons from one place to the other. So in the battery right there, you can see there's like a negative side and a positive side. Electrons are being generated at that negative symbol right there. So that's the site of oxidation. And electrons will go through the wire to the other side, the positive side. Electrons want to go there. That's the side where the reduction is occur. But you can see that in the middle they have a type of a switch, like a way to turn the reaction off and on. When the wire isn't connected, the light bulb is off. When it is connected, the light bulb is on. So when the light bulb is on, that just shows that your reaction is going. Something's happening. And if the light bulb, of course, is not on, then you don't have any electron transfer. So you can literally control the electrons going from the site of oxidation to the site of reduction. And that's what an indirect redox reaction is all about. You can use that chemical electrical energy to do some really fantastic things. Why study electrochemistry, you might be thinking? Oh, there's nothing really that important or anything like that. Just, batteries. Okay, everybody uses batteries. Phones, computers, you name it. Everything's got batteries. And batteries is a reason enough to study electrochemistry. Corrosion is a big part. From Navy ships to cars at the ocean, everything can undergo corrosion on one level or another. And if you understand electrochemistry, you can help prevent the corrosion, especially if it's something really important like an aircraft carrier or whatever, or even an old car. They're really important too. Industrial production of chemicals. In the chemistry lab, we, if this has been a face-to-face lab, we've used like sodium hydroxide and other kind of chemicals. A lot of those chemicals are made in the lab through electrochemistry. We'll talk a little bit about that at the end of this chapter, but needless to say, it's kind of important. But gosh, most important of all is that you've all been using biological redox reactions as we watch this video. The heme group, which has iron in the middle of it, is a great example of how this works. The iron takes oxygen from the air and then it releases it later on. That's a redox reaction as well. So biology is filled with redox and your life is then too. Lots of reasons why you should be interested in studying electrochemistry besides just, getting a good grade or for pure scientific interest, which anyway, enough said. An electrochemical cell is just a way that you can separate out the oxidation part from the reduction part. So in a battery, there's basically an electrochemical cell, and you can somehow control how the electrons go through within the batteries itself. There's different kinds of electrochemical cells. Most of the time in this chapter, we're going to look at product-favored reactions, and those just mean batteries that work. All right. You put them in something and they start, making the flashlight go, or your cell phone operator or whatever. So product favored electrochemical cells, product favored reactions in a battery are called voltaic or galvanic cells, and they create usable electrical current. All right. So if you have a battery that works, you have a voltaic or galvanic cell. You can use either name. Those are named after some famous electrochemists we'll see. So all working batteries are voltaic or galvanic cells, and these are the kind of batteries we usually want to operate our different widgets. There is, though, use in talking about reactant-favored reactions. These are batteries, quote unquote, that if you plug them in, nothing happens. These are called electrolytic cells. Now, believe it or not, these are useful for different processes, especially for making chemicals, because if you apply electricity to an electrolytic cell, you can make those things happen. They don't happen by themselves, but they will happen if you apply electricity. Now, after our last chapter, you can probably see that voltaic and galvanic cells, which are product favored, are going to be spontaneous. Their delta G value will be negative. On the other hand, reactant favored reactions, ones that don't work when you plug them in, those are going to be non-spontaneous. Their delta Gs are going to be positive. We'll talk about that more later.